Hello everybody, my name is Ethan. Welcome back to the machine learning course on Codecademy. In today's video, we're going to be talking about boosting. In the previous video, we did the start of the ensemble methods in machine learning with random forests, which was a very long video. It ended up being around an hour and a half, so probably the longest video we have on this playlist. So if you missed that one, be sure to go check it out. Don't watch the whole thing in one sitting, but go make sure to watch it. Gives you a little bit of insight into what we're doing. In this part of the section, we're going to be going into boosting. So what is boosting, all that type of stuff. So let's get into it right away. Without further ado, boosting. In this module, we'll cover a powerful ensemble method called boosting. Boosted ensemble methods use weaker learners as base models that are simple and tend to suffer from high bias. The weak learners underfit the data. Boosting is a sequential learning technique where each of the base models build off the previous model. Each subsequent model aims to improve the performance of the final ensemble method model by attempting to fix the errors in the previous stage. There are two important decisions that need to be made to perform boosting ensembles. One is sequential fitting method, and two is aggregation method. Two boosting algorithms that will be covered in detail in this module are adaptive boosting and gradient boosting. While boosting can be applied to any base machine learning model, we will demonstrate this with an extremely popular choice as a base estimator, the decision tree. Recall that decision trees are commonly used in powerful machine learning algorithm because they are easy to interpret. Additionally, the training data requires very little manipulation, so no need for standardization or removal of collinearity. The major limitation to decision trees is that they tend to suffer from high variance and therefore prone to overfitting. They are good at making a series of decisions which cause them to memorize the training data, so they do not generalize well to unseen data. In the following exercises, we will explore how to work past these limitations while using decision trees for boosting. We have a nice little interesting thing. We again covered bagging in the previous video, so be sure to check that out. Adaptive boosting overview. Adaptive boosting, or ADA boost, is a sequential assembling method that can be used for both classification and regression. It can be used on any base machine learning model, though it is most commonly used with decision trees. For ADA boost, the sequential fitting method is accomplished by updating the weight attached to each of the training data's set observations as we proceed from one base model to the next. The aggregation method is a weighted sum of those base models where the method or the model, see I said model for when it was method for when it was model, don't know why I'm doing that. The aggregation method is a weighted sum of those base models where the model weight is dependent on the error of that particular estimator. The training of an ADA boost model is the process of determining the training data observation weights at each step, as well as the final weight for each base model for aggregation. In the next exercise, we will dive into the details of ADA boost. All right, adaptive boosting. Let's take a deeper look at how this works. ADA boost can be used for both regression and classification, but in this example, we will be solving a classification problem. We'll begin with the full training data set. You will see that it consists of green circles and red triangles. The goal of our ADA classifier will be to form a decision boundary that separates the two classes. Initially, the training data instances are all given the same weight. This is indicated by the size of shapes all being the same size. Our first step is to fit the estimator, the first base model. While boosting can be applied to any base machine learning model, we will use decision trees. But aren't decision trees prone to overfitting? We already said that because that the base models for boosting are supposed to be very simple and tend to underfit. That is correct, and for this reason we use the simplest version of a decision tree known as a decision stump. A decision stump only makes a single decision, so the resultant estimator only has two leaf nodes. Taking a look at the result of the first base model, we see that the decision boundary, that is the border between the lighter green and lighter red regions, does a decent job of separating the red circles from, or the green circles from the red triangles. However, we do notice that there are two red triangles in the light green region. This indicates that there have been that they have been classified incorrectly by the decision stump. Right here and here. Each of the base models will contribute a different amount to the final ensemble model. The influence that a particular base model contributes is going to be dependent on the number of errors it makes, or for regression, the magnitude of errors it makes. We do not want a decision stump that does a terrible job of classifying the data to have the same say as the decision stump that does a great job. Once we are able to evaluate the result of the first base model, we can weight the model and assign it a value here indicated by alpha 1. So again, we have the training data. We fit that model to our first base model. That model gives us a result where we have two triangles that are kind of incorrect. That gives us our alpha 1 weight. And now we're going to re-weight the data to tell us that, oh, those ones that were incorrect should be weighed more. And now we have, basically alpha 2. So we're going to see that it goes again. Taking a look at the result of the second base model, we see exactly what happens. The two larger red triangles are classified correctly by the second base model. Once again, we assign a base model of weight alpha 2 proportional to the errors it makes and prepare for the next stage of sequential learning by reweighting the training data. The instances that were correctly classified by the second base model, the two green circles in the center, are given a larger weight. Once we have reached a predefined number of estimators for our ADA boost, the base models are ready to aggregate. In this example, we've chosen n estimators equals 3. The influence of each base model in the final ensemble model will be proportional to the alpha. So again, we reweight it one more time, and we'll find that, okay, we still have 1 in here. So now we end up getting an ensemble model where we aggregate all of those first base models into one that kind of makes sense, right? So we get alpha 1 weight model, we reweight it so that these two triangles mean more. Then we see the circles are incorrect, so then we update the circles instead, and we get our third, and now it draws the line nicely. Adaptive boosting implementation. Wow, that was a lot to take in. Let's take this opportunity to implement ADA boost on a real data set and solve a classification problem. We'll be using data set from UCI's machine learning repository to evaluate the acceptability of a car based on a set of features that encompass their price and technical characteristics. So it wants me to create the base estimator for the ADA boost classifier in the form of a decision stump using decision tree classifier and store it in the variable name decision stump. Recall that a decision stump is a decision tree with only 2 leaf nodes. It wants me to then print the parameters of the decision stump using the .getParams method. So it wants me to first create a decision stump and set that equal to a decision tree classifier. And for right now, I'm going to leave that blank. And then it wants me to print the decision, decision stump.getParams. It's running. We'll see if it ends up going. Oh, max depth equals 1. Oopsie. We're specifying 1 because it's a stump, so it's only going to have 2 leaf nodes, so just 1 depth, right? All right. Using ADA boost classifier, create an ADA boost classification model with the base estimator parameter set to decision stump and n estimator set to 5. Store the model in a variable called ADA classifier. Print the parameters using the .getParams method. So we'll create a new classifier called ADA classifier. Set it equal to the ADA boost classifier with the base estimator. We don't have to specify the names, but we will for the sake of learning here. So we know what each one does. Decision stump, and then n estimators is equal to 5. We'll store it in that, and then we'll print print ADA classifier dot get params. We now want to fit the ADA boost classifier to the training data and get a list of the predictions. So we'll fit it. We'll do ADA underscore classifier dot fit, and we're going to fit it to X train and Y train, which are specified right here. And then what it wants us to do is predict the classes of the testing data set and store them in an array named Y prediction. So y prediction is going to be ADA classifier dot predict using the x testing variables. Oh no, it wants me to actually. Oh no, I'm doing it right. Never mind. So we can click run now. Now we will explore some of the most common evaluation metrics for our classification on our trained ADA boost model, calculate the accuracy, calculate the precision, recall, and the F1 score. Remove the comments from the code block to print the evaluation metrics you just put. So it wants us to first create an accuracy, and we'll set that equal to, I believe it's, accuracy underscore score of y test and y prediction. Then we will do the same thing for precision, but instead it's going to be precision underscore score, precision underscore score with y test and y prediction. And we'll do recall is equal to recall score with, of course, y test, not y minus test, y underscore test, and y underscore prediction. And finally, we'll do the F1 score, which is just F1 underscore score as F1, and we'll say F1 score with y test and y predicted. Then it wants me to uncomment all of these lines right here so that we print it out and see what it looks like. So when we print this out, we see that the test set accuracy is 85%, the precision is 72%, the recall is 83%, and the F1 score is roughly 77%. So then it wants me to take a look at the confusion matrix by uncommenting the appropriate lines here. If we do that, we can say that test equals confusion matrix. It wants me to do, oops. And then it wants me to print confusion matrix. And this is what the confusion matrix looks like. So a lot of good predicted no, actual no. When we have these two as the highest, that's obviously the good thing, right? Because that means we get true positives and true negatives, right? So, all right, gradient boosting overview. Gradient boosting is a sequential ensembling method that can be used for both classification and regression. It can use any base machine learning model, but it's most commonly used with decision trees known as gradient boosted trees. For a gradient boost, the sequential fitting method is accomplished by fitting the base model to a negative gradient of the error in the previous stage. The aggregation method is a weighted sum of those base models where the model weight is constant. The training of a gradient boosted model is the process of determining the base model error at each step and using those to determine how to best formulate the subsequent base model. In the next exercise, we will dive into the details of gradient boosting. Gradient boosting. Now we will take a look at how gradient boosting works. So while gradient boosting can be applied to any base machine learning model, decision trees are commonly used. Our first step is to fit an estimator. The first base model, recall that the base estimators for boosting algorithms tended to be simple and high bias. In contrast to ADA boosting, which leveraged the simplest form of decision trees, the decision stump with only one level, gradient boosting can and actually do tend to include a few more decision branches. Often, gradient boosted trees will have up to 32 leaf nodes, which corresponds to a tree depth of 5 levels. In this example, we are limiting the depth of the base estimators to 2, corresponding to 4 leaf nodes. Once the first base model is trained, the residual errors, h_1 of the model given the training data are determined. The residual error is the difference between the actual and predicted values for each of the training data instances. So h1 is equal to y actual minus y1 predicted. The errors will be greater for the training data instances where the model did not do as good a job with its prediction, and will be lower on training data instances where the model fit the data well. In the next stage of the sequential learning process, we fit the second base model. Here is what the interested part, here is where the interesting part comes in. Instead of fitting the model to the target values y actual as we are typically used to doing in machine learning, we're actually going to fit the model in the areas of the previous stage, in this case h_1. The second base model is literally learning from the mistakes of the first base model through those residuals that were calculated. The results of the second base model are multiplied by a constant learning rate alpha and added to the results of the first base model to give the set of updated predictions. The results of the second base model, which was tasked with fitting the errors of the first base model, are multiplied by a constant learning rate alpha and added to the results of the first base model to give us a set of updated predictions y_2 predicted. The residual errors of the second stage are calculated using the updated predictions to get h2 is equal to y actual minus y2 predicted. The subsequent stages repeat the same steps. At stage n, the base model is fit on the errors calculated at the previous stage, h_n-1. The new model that is fit is multiplied by the constant learning rate alpha and added to the predictions of the previous stage. Once we have reached the predefined number of estimators for our gradient boosting model, or the residual errors are not changing between iterations, the model will stop training and we end up with the residual ensemble model. So we get our first base model. We calculate our residuals. We then take our first base model and add alpha times the residuals, and then calculate the residuals after that. Then we keep and continuing that process until we finish with the nth base model. All right, gradient boosting implementation. Now that we've taken a look at what's going on under the hood, we are ready to implement gradient boosting on a real data set and solve a classification problem using a data set from UCI's machine learning repository to evaluate the acceptability of a car based on a set of features that encompass their price and technical characteristics. So, first thing that wants me to do is create a gradient boosted trees classification model using gradient boosting classifier with n estimator set to 15. Leave all other parameters set to their default values. Store the model in a variable called grad classifier. So we'll say grad classifier is equal to gradient boosting classifier with the value of n estimators equaling 15. It then wants me to print the parameters, so we can print grad classifier dot get params, and that should print all the parameters you can put into the grad classifier. So we can see all of them there. Fit grad classifier using the training features xtrain and corresponding labels ytrain, and then predict the classes of the testing dataset xtest and store them in an array of a variable called yPrediction. So we'll first fit it. We'll do grad classifier dot fit, and we're going to fit this to the training data and training labels. Then we'll create a new array called yPredicted and set that equal to grad classifier dot predict using the x testing data. Predict the game. Okay. It now wants me to do the same thing that we did previously, right? So create the variables accuracy and set that to the accuracy score of y test and y prediction And we can do the same thing for precision. Then same thing for recall. Very similar to what we did in the previous one, except this time we're doing the gradient testing instead of the boosting testing. Okay, and then we can uncomment the lines here that print out all of that. We'll end up seeing all the information here. After it loads, of course. We ended up having an accuracy of 89%, precision of 78%, recall of 89%, and F1 score of 83%. Take a look at the confusion matrix by removing the comments and relative code. Oops. The confusion matrix now looks like this. And again, these two numbers are good. So that's kind of what you want to see, right? All right, up next. We do have a quiz. So there's two leaf nodes and a decision stump, right? Fill in the missing text in the following paragraph about boosting. Boosting is an ensemble learning where leak learners are too high. Decision trees are a common choice because they need to be super based on one feature causing them to are too where the weak learners are too simple and tend to suffer from high, I want to say it's bias, causing them to overfit the data. It's going to be wrong, unfortunately. Decision something else, not trees. Stumps. It would have been stumps. And it's going to be underfit. Oops. And there's only 5 questions, so we might have to redo this one. For the gradient boosting classifier, the default value of max depth is 3. What is the maximum number of relief loads of a depth that depth can have? So 2, 4, 8. Yep. Fill in the text. Bagging methods use only a subset of available features and a subset of draining data due to bagging methods use weak learners. I think it's strong learners that are complex because this is the whole lesson, what it's about. And tend to suffer from high variance. Their weakness as a model is due to the fact that they're built with only a subset of the available features. And on a I hate that. We'll have to redo this one. Which of the following statements about ensembling is false? Base models for boosting are chosen to be simple. Base models should be correlated and improve the ensemble model. High diversity is false. Base models can be weak learners. That's true. High diversity among base estimators leads to a stronger ensemble. True. Base models should be correlated and that improves. Base models are boost. This one, right? Yeah. All right, we're going to have to retake it, unfortunately. Decision stump has 2. Boosting, where the learners are 2. Yeah, it was decision stumps. High bias, causing them to underfit the data. Simple. Cool. 8. Bagging method use weak learners as base models that are complex and send high variance on the subset of the data due to bootstrapping. Cool. True. True. They don't need to be correlated. Okay, cool. Let's do the project now. Boosting project. Census data, predict if they make more than $50,000 or not. We're going to see if we can do this one. If you watched the last video, you would have known that it was a little bit tricky because they left out a lot of stuff that I thought we needed. Okay, take a look at the distribution of the target column income. Which percentage of samples have incomes greater than less than equal to 1? Okay. Percentage of samples. So if we do... we're going to want to select the column, right? So we'll do df data frame with the income column dot value counts, and we print that out. We'll end up seeing the listing of, hopefully, yep, looks like that. So it's asking us what percentage of samples have higher income. If we grab 0, what happens? We should see 24,000 is what I'm going to assume. Object is not subscriptable, unfortunate. So then it's $50K. Does that work? Oh, what am I doing? I'm putting it outside of the print statement. That's why it's not subscriptable. What am I doing? Putting the print statement like that. That was stupid. This should work now. Yeah, so we see the 24,000. Basically, what we can do is, so less, we'll call this a variable less than, we'll create a variable more than is equal to data frame, very similar with income, dot value counts, and then subscripted at greater than, I think it's just called greater than or equal to, not greater than or equal to, just greater than 50, okay. Then we'll say less than percentage is equal to less than divided by df income dot, I think I can just do dot sum, and then more than percentage is just going to be the more than divided by the df income dot sum, and then we can print we'll print percentage of samples that have income percentage of people with income greater or less than 50K, and then we'll put in the less than perc And then we'll do this, percent of people with more than 50K, more than perk. Let's see if I did it right, guys. I mean, I'm sure I'm going a little bit more complex than I should have on step 1. Okay, of course. True divide not supported. So can't do the sum. Can we do dot value counts dot sum? I'm sure I should be able to do that. Come on now. Cool. And it looks like these add up to roughly the same things. That makes sense. Ended up doing that one right. Okay. We can now look at number 2. We have identified that a set of features to explore. The features are stored in the variable raw features columns. We actually do have it this time, which is something. We've identified the features. Take a look at the data types of the column. Are they what you expected based on the data dictionary provided in the description? So we go to features. The features are stored in a variable. Take a look at the data types of these features. What's it called? Raw feature calls. We want to print. Would it just be feature.d type? Command Python command for seeing data type. Let's just type. Print. I'm gonna say print feature, and then print type of the feature. Okay, cool. So we have age is a string. They all are strings. So that obviously doesn't seem right. You know, age should probably be an int class, right? So create a features data frame X with the features listed in the stored variable raw features. Since the columns work class X and race are all low cardinality, categorical variables, convert them to W rows, get dummies. Set the parameter drop first equal to true, mp.get dummies. This drops the first categorical instance of each of the categorical variable columns because it is redundant. Make sure you understand why we do not have to worry about dropping the redundant variables before moving on. Note pd.get dummies is clever enough that it will only create dummy variables for the categorical columns, would not create dummy variables for the int64 columns. Take a look at the first 5 rows of the features data frame using the .head n equals 5. Okay. For right now, I'm going to get rid of step 2 just so we're not completely clogged in our console. I will keep up this, though, just because I think it's a good idea to. It wants me to prepare the features, though, by using the .get dummies command. So we can do pd.get dummies for the features in raw features calls, and then we'll say drop first equals true. And we're going to set this equal to capital letter X, and I think that should be fine. And now we can also do x.head, put the int 5 in it. Something I did wrong, though. Raw features calls is not defined. Interesting, because it's right here. Is it raw? It's just raw feature. And then if we do x.head5, it'll print out the first 5 rows of the columns. Or of this new pandas data frame here. And it looks like we have this looking correctly. Looks nice. Okay. Convert the target variable to a binary value and store it in the variable y. Set it equal to 0 when income is less than 50K and 1 when, okay. So we want y to be equal to, it's probably going to want me to do numpy.where if I had to guess. Oh. This is the hint for this one. Perform a train test split. Am I doing the wrong variable here, maybe? Oh. I see. Data frame. I don't know why I wouldn't have. To prepare the features. Yeah, this hint is not useful at all, obviously. np.where. What did they do? Let's see. I assume it would be an np.where is what they would have done. Yeah, np.where is equal to, see, it's very interesting syntax. So y is equal to np.where data frame target column. Do we already set target column equal to something here? I assume we did when we went, yep, target column. So we'll say np.where data frame target column and equals the string less than or equal to 50K, and then it said it wanted a 0 and a 1. Create train est split. Train test split, we'll correct them here. Wants me to perform a train test split, so we can do x train x test y train y test is equal to train test split based on x and y, and then it wants it at a classifier in the form of this. And it didn't specify what percentage, but when I looked at the hint in step 4, it says test size equals 30% is equal to 0.3. Okay. In step 5, though, it wants me to create a base estimator for the ADA boost classifier in the form of a decision tree stump using decision tree classifier and store it in the variable name decision stump. So decision stump is equal to decision tree classifier, and we remember that when it's a stump, it's got a max depth of 1. Now it wants me to create an instance of ADA boost classifier and store it in ADA boost classifier. So we can do that by doing ADA classifier is equal to ADA boost classifier with the value of decision stump, and everything is default except we'll specify for sure that base estimator is equal to decision stump. Okay, now it wants me to create a gradient boost classifier. So we'll call that grad classifier, and it wants me to keep all default values. So I'll leave it as that. So next it wants me to fit each of the instantiated models on the training data, calculate and score the predictions of the test data in separate variables, ypred ADA, ypred grad, print the accuracy and F1 score of each of the predictions in the model. So first it wants me to fit the models and get the predictions. So we'll first do the first one, which is ADA classifier. We'll do .fit. We're fitting it to the X train and Y train data. Then we'll do grad classifier. We'll do dot fit to the x train and y train data. Then it wants me to create the two variables of y prediction ADA. That's going to be equal to ADA classifier dot predict using the x testing data. Then we'll say y prediction of grad is equal to grad classifier dot predict using the x testing data like before. Finally, we can print the accuracy and F1 score of the separate models by first creating variables accuracy ADA. I'm going to say is equal to accuracy score of y test and y prediction ADA. Then we'll say accuracy of grad would be equal to the accuracy score of y test and y predicted grad. Finally, we're also going to want to do the F1 score, so we can say F1 of ADA is equal to F1 score with y test and y predicted ADA. Then we have the F1 score of grad, which is equal to F1 score of y test and y predicted grad. Okay, a lot of typing there. That's okay. We're okay with typing. We're now going to print these out. Print F. We'll say accuracy. Let's see. ADA accuracy. Accuracy underscore ADA and F1 score. Oh my. And then we can do F1 ADA. I am going to just copy this, paste this, ADA accuracy. This should be now grad accuracy. And F1 score, which would just be F1. Okay, so hopefully we did that correct. I'm really hoping so because that was a lot of typing and I don't want to redo it all. Okay, gradient boost classifier is not defined, and that is in line 65, which is right here. Is it an A? Is it me misspelling it? Gradient boosting classifier, not just boost classifier. That's obviously a mistake, so we can fix that pretty easily by just putting in an ing where it should go. Now let's see, hopefully we print out the ADA accuracy and F1 score. All right, awesome. So for our ADA accuracy, we got it 80% and 52% F1 score. And for the grad accuracy, very similar, 81% and 52% grad F1 score. For ADA boost, so we can explore hyperparameters here. For ADA boost, the default N estimators is 50. We've created a new list here of N estimators to search. Use grid search CV with ADAV. I'm going to skip this for right now just because I want to move on from this. But if you did enjoy this video, please be sure to give it a like, subscribe. And I think, yeah, oh, well, we might have just one little article here at the end. We have some sort of stacking article. We talked about stacking in the last video. If you missed that, be sure to go check it out. I don't think conclusion, we've covered in depth how stacking can combine predictive power. Yeah, we don't need to learn about this one too bad, and that is okay. Sorry about the Discord notification. Let's see what's up next here. This is going to be kind of the home stretch here. As you can see, it looks like we have one more chapter, which is the build machine learning pipelines. And then we kind of have stuff where it's 1 minute, less than a minute. So probably going to get finished either today or tomorrow. If you did enjoy this video, please be sure to give it a like, subscribe, and I'll see you in the next one. Peace out.